everybody. So today we are starting our first set of notes, which is section 5.1, which is all about the nth roots, radicals, and rational exponents. So as a warm-up, please complete problems 1, 2, and 3. So pause the video because I'm going to show the answers in 3, 2, 1. All right, so for number 1, we got 15. For number 2, we got 3 square root 3. And for number 3, we got 2 square root 33. So when you're simplifying the following radicals, which were all square roots, we were looking for those perfect squares. So what number times itself? And we were able to simplify those perfect squares. So today we're going to be simplifying nth roots, so not necessarily square roots. The reason the square root of 225 is 15 is because 15 to the second power is 225. Square roots and squaring are inverse operations of each other. When multiplying nth roots, you're looking for what number raised to the nth power. The easiest way to do this is to find the prime factorization of the radicand. And that's like what we were doing up in our warm-up. We were making the factor tree. We were finding the prime factorization of each number. 27 is 3 to the third power, etc. So same process, but instead of finding perfect squares, we might be finding perfect cubes or perfect fourths, depending on what the nth root is. So let's take a look at example number 1, the cubed root of 64. So we have the cubed root of 64. I know 64 is divisible by 2, so that's 2 and 32. I know 32 is divisible by 2, so that's 2 and 16. I know 16 is divisible by 4, so that, by 2, so that's 2 and 8. And I know 8 is divisible by 2, it's 2 and 4, and keep going, that's 2 and 2. So we have the cubed root, so we're looking for perfect cube. So I have a 2 times 2 times 2. There's a perfect cube there. And 2 times 2 times 2. There's another perfect cube. So I can pull 1, 2 out and another 2 out, leaving us with 4. And nothing left underneath the radical since there are no more factors left of 64. If you're very good with perfect cubes, you might have noticed that 64 is 4 to the third power, which is why the cubed root of 64 was 4. But it's not always easy to see that, which is why we have the factor trees to help us out. So let's go ahead and let's do example number 2. The fourth root of 81. So 81 I know is divisible by 9, 9 and 9, 9 I know is 3 and 3, and 3. So there we go. We have that broken down into the prime factorization because 3 is a prime number. So fourth root, I'm looking for perfect numbers raised to the fourth power. So I have 3 times itself 4 times. So the fourth root of 81 is 3. And again, if you're good with your factorizations, you might have known that 3 to the fourth power is 81, which is why the fourth root of 81 is 3. But again, if you didn't know that, that's okay. That's why we have the factor trees. Since we're now taking odd roots, like we saw in the last example, we took the cubed root of 64, we can simplify nth roots of negative numbers, just as long as n is odd. Because if I have a negative times itself an odd number of times, I know that I have a negative result. So, for example, number 3, the fifth root of negative 243, I can do this because I have an odd root of a negative number. So, just like with the other examples, we're going to build our factor tree. When I build my factor tree, I kind of ignore the negatives until the end. So 243, I know that's divisible by 3. One and 3, I know, is 9 and 9, which is 3 and 3, 3 and 3. So fifth root, I'm looking for 5 of a kind. So I have 1, 2, 3, 4, 5. There we go. I have 3 times itself 5 times. So the fifth root of negative 243 is negative 3. And again, the reason why is because negative 3 to the 5th power is negative 243. Let's look at example 4. So again, I'm taking the cubed root. So right away, I have a cubed root of negative, which is fine because it's an odd root. So I'm going to pull the negative out to the answer, so now I don't have to think about it. So 64 is 2 and 32, which is 2 and 16, which is 2 and 8, which is 2 and 4 is 2 and 2. So cubed root, I'm looking for 3 of a kind. So I've got a 2 there, and another 2 there. So I can pull out a 2 and another 2, so I end up getting negative 4. And again, the reason why is because the cubed root of negative 4 to the 3rd power, or negative 64 is negative 4 to the 3rd power. Converting between radical form and rational exponent form. So recall from Math 2 Honors that x to the power of m times n is the same thing as the nth root of x to the power of n. Or we could replace the order and say it's also the same thing as the nth root of x raised to the mth power. And as we saw in our Unit 4 group challenge, negative exponents just mean you need to reciprocate the value. So if I have x to the negative m over n, that just means 1 over the mth root of x to the m, or 1 over the mth root of x all to the mth power. So let's practice just switching between forms. So example number 5, write each expression in radical form. So I have a to the 1/5 power. So remember, x to the power of m over n is the same thing as the nth root of x to the power of m. So a to the power of 1 over 5 is the same thing as the 5th root of a to the 1st power, or the 5th root of a. Let's take a look at number 6. Again, remember x to the power of m over n is the same thing as the nth root of x to the power of m. So the 7 to the power of 2 over 3 is the same thing as the cubed root of 7 squared. Or, if you chose to write it in the other form, we have the cubed root of 7, that whole thing squared. Either one of those is a perfectly acceptable answer. This one, or. So let's go backwards. Let's say that we have the cubed root, write each expression in exponential form. So let's say we have the cubed root of b. So remember, x to the power of m over n is equal to the nth root of x to the n. So b, since I don't see an exponent, is actually being raised to the 1st power. So this can be rewritten as b to the power of 1/3. This is really helpful when you are doing calculator work, because finding the cubed root in your calculator might take time, but raising a number to the 1/3 power takes 5 seconds. Similarly, on number 8, remember x to the power of m over n is the same thing as the nth root of x to the power of m. So I can rewrite the fourth root of p to the 7th as p to the power of 7 over 4. Clean that up, make it look a little bit better. 7 over 4. So understanding that relationship between the radical form and the radical form, radical form and exponent form, helps us then simplify various rational exponents. For example, number 9, 25 to the 1/2 power. If you are good with your properties of exponents, could use your properties of exponents. 25 is 5 to the 2nd power. Power to a power we multiply. So this is 5 to the 1st power, which is just 5. Or we could use the fact that x to the power of m over n is the same thing as the nth root of x to the power of m. So I could rewrite 25 to the 1/2 as the square root of 25 to the 1st power, which is 5. We're going to skip number 10 for time purposes. All right, number 11. So negative 27 to the 1/3 power. Using that relationship, I can rewrite this as the cubed root of negative 27. So from here, I can simplify. That's going to be negative. Since it's an odd root, I can take the cubed root of a negative number. That's 3 times 9, which is 3 times 3. So we end up getting negative 3 as our answer. Cubed root, we're looking for 3 of a kind. All right, number 12, I can rewrite this as the 4th root of 625. So I know 625 is divisible by 5. Chosen 125 times. I know that's divisible by 5. Chosen 25 times, and 25 I know is 5 times 5. So 4th root, I'm looking for what number times itself. 5 times, yikes. So this is 5. All right, number 13. The 4 to the power of 3 over 2. So again, using those properties, I have x to the power of m over n, which is the same thing as the nth root of x to the power of m. I can rewrite this as the square root of 4 raised to the 3rd power. The square root of 4 is 2. 2 raised to the 3rd power is 8. Negative exponents just mean we have to reciprocate. You got to move it to lose it. So I can rewrite this as 1 over the square root of 9, which is 1 over 3. Number 15. Again, we're going to skip for time purpose. Oops. Number 16. So negative exponent means I got to move it to lose it. So I move the 32 to the denominator, and now I have a positive exponent. So this is really 1 over the 5th root of 32 to the 3rd power. So 32 is 2 times 16, which is 2 times 8, which is 2 times 4, which is 2 times 2. So 5th root, see, 1, 2, 3, 4, 5. Perfect. So the 5th root of 32 is just 2. 2 to the third is 8. So we get 1 over 8. And again, we're going to skip 17 for time purposes. And let's finish up with 18. So I have 1 over 27 to the 2/3. So that's really 1 over cubed root of 27 squared. So 27 is 3 times 9, which is 3 times 3. So the cubed root of 27 is just 3, and then 3 squared is 9. So we get 1 over 9. All right, now we're going to be simplifying nth roots with variable expressions. So the properties of rational exponents and radicals can also be applied to expressions involving variables, because a variable can be positive, negative, or 0. Sometimes an absolute value is needed when we're simplifying a variable expression. So if we're given x to the power of m over n, which again is the nth root of x to the m, or the nth root of x, all of that to the power of m, if n and m are both even, but simplified to be odd, then an absolute value is needed. And here's why. So the square root of 4x squared is 2x. But we don't know what x is. X could be positive, x could be negative, x could be 0. So if x were negative 1, then, and we say that the square root of 4x squared is equal to 2x, when we plug in negative 1, I get square root of 4, which is 2 on the left-hand side, but negative 2 on the right-hand side, and that ends up giving us a false statement. So what we do is when we have a even root with an even exponent, both are 2, that simplify to be odd, x is now to the first power, we have to add absolute values around that. So that in this case, if let's say x were to be negative, we would get the square root of 4, which is 2, and here we would have 2 times the absolute value of negative 1, which is 2 times positive 1, which is now 2. And now we have a true statement. All right, so let's go ahead and do problem 19. The cubed root of 8x to the third. So the cubed root of 8, break 8 down, that's 2 and 4, which is 2 and 2. So 8 is really 2 to the third, and x is to the third. So the cubed root of 8x to the third simplifies to be 2x. I don't need an absolute value since it's an odd root. And just like the cubed root of 2 to the third is 2, the cubed root of x to the third is x. All right, let's take a look at number 20, the cubed root of 32x to the 6th. So 32 is 2 times 16, 2 times 8, 8 is 2 times 4, and 4 is 2 times 2. Ooh. This one got on there by accident. We were only supposed to have perfect cubes. So cubed root means what number times itself 3 times. So I have the cubed root of 32. I can pull a 2 out, but I still have this 2 times 2 left over underneath the radical. X to the 6th is x to the third times x to the third. Properties of exponents, when you multiply, you add. So I can break x to the 6th up into 2 sets of x to the third. So I can take that one out and that one out. So we're left with an x, and I can take one more x out, since again I have two sets of x to the third. So we get 2x squared on the outside, and the cubed root of 4 left over. And that's kind of a peek into what we're going to be doing on Monday. All right, we're going to skip 21 for time purposes, and let's take a look at 22. So 22, I do have a even root with even exponents. So if any of these do simplify to be an odd exponent, I am going to need absolute values. So let's break up x to the 20th. X to the 20th is, let's see, 1, 2, oops, we do that. 1, 2, 3, 4, 5 sets of x to the 4th, and y to the 8th is 1, 2 sets of y to the 4th. So I can take out 1, 2, 3, 4, 5 x's and 1, 2 y's with nothing left over. So since I had an even root with an even exponent, and I did have the x's simplified to an odd power, I do need an absolute value around that x. All right, 23 is the cubed root of negative 8, a to the third, b to the third. So again, simplifying the cubed root of negative 8. 8 is 2 times 4, which is 2 times 2, so 8 is 2 to the third. And b to the 9th, I can break up into 1, 2, 3 sets of b to the third. So this simplifies to be negative 2, a, and I can take out 1, 2, 3 b's. So negative 2a b to the third. I don't have to worry about absolute values since I have an odd root. And finally, number 24. Let's break down 256. So 256 is divisible by 2. That goes in 128 times. That's divisible by 2. Goes in 64 times. 2, 32, 2, 16. That's 2 and 8, which is 2 and 4, which is 2 and 2. So I'm taking the 4th root, so I have 1, see, 1, 2, 3, 4, 2 sets. So 256 is made of 2 sets of 2 to the 4th. X to the 12th is 1, 2, 3 sets, because again, that gives us 4 plus 4 plus 4, which is 12. So that's x to the 12th. And y to the 24th, let's see, that's 1, 2, 3, 4, 5, 6. So I can take out a 2 and another 2 and 1, 2, 3, 4, 5, nope, sorry, 1, 2, 3 x's. Those are my x's. And then for the y's, I have 1, 2, 3, 4, 5, 6. Those are my y's. So this simplifies to be 4x to the third, y to the 6th. I did have an even root with an even exponent, so I do need a set of absolute value bars around x to the third, since that one came out to be an odd exponent. All right, have a wonderful day. I hope you found this video informative, and Good luck with your homework tonight, and I will see all of you guys on Monday, or sorry, Friday. Bye.